Hi everyone, welcome to my video on energy conservation with non-conservative forces. So in this video, what I'm just going to talk about is the ability to identify non-conservative forces, more specifically how to deal with them in our energy conservation equations that we're going to be modeling our systems with. So like I mentioned here in the bullet points that I have, I'm going to talk a little bit about them and talk about what happens when you have work done on the system, and then how to add work into your energy expression, solving work, and then just kind of looking at some bar graphs that we can make with these. So let's go ahead and move forward. So I know there's a lot of writing right here, but basically all I'm saying in this is if there's no work done on the system, in other words, no one's pushing the system or friction is not acting on the system, then the total energy is conserved. So the total mechanical energy is transformed from one form to another, and those forms remain unchanged. So of course some of our biggest examples is the the PhET simulator, right? The PhET skate park. The PhET skate park without friction, we saw that those energies kind of balance themselves out and that the total energy remained the same. So mathematically we can model this a few different ways. They both really mean the same thing, but the initial energy equals the final. Or if I move the initial over, the change in the two should be 0. So if we do work on the system, the energy is not conserved. So in other words, we actually change the amount of mechanical energy of the system. So your system initial is not the same as the final. And what happens is whatever the change is, so kind of remember that change in the total mechanical energy, that's going to be the final minus the initial, right? Any change is final minus initial. Well, there's going to be some leftover work done in this case because they actually won't equal each other. So that's what happens. And then, like I said, the mechanical energy actually changes in your system. So if your final is smaller than your initial, then you'll have a negative work. So the energy is removed from the system. So this is if your initial velocity, for example, just using speed as an example, it's not the only example. If your initial velocity is way less than what it should have been, then that's when work is negative and being taken away from the system. You could have the opposite case. You could have more energy than you started with. That's fine if you add work to the system. So this is like when you, like I said, when you like push yourself or add an applied force. So this is how you model work in an energy conservation system. And I hope you noticed I didn't really define this, but WNC is work by a non-conservative force, so non-conservative. So honestly, you can model this many different ways. I'm showing you a few different ways to think about this. That the total final energy minus the total initial energy equals the work done by the non-conservative force. Or kind of the way I write it is kind of like this setup, the second line right here. If you notice, I have the initial energies plus whatever work is done is equal to the final. So it's kind of the form that I typically use. So the sign, of course, changes depending on what happens. So the sign of work will be positive if you're pushing or applying a force. So that's going to add, speed to your object typically. Like a skier like kind of like pushing on snow, right? So if I were like a skier and I apply a force over some distance and it's in the same direction, we know that's going to be some positive work done in the system. And I'm going to be adding energy. If the sign is negative, if you have friction, you're going to lose energy, so your sign will be negative here. So the signs depend on what's happening. And like I said, honestly, friction is your biggest contributor to energy losses in the system. Now, friction, as you saw in the in the skate park scenario is this is actually a form of thermal energy, because friction actually heats things up. So in a more, abstract sense, this is where the energy goes to thermal, but friction takes away energy. That's fine. That's all we need to really know. So something also too is usually when we study our systems, this is not always true, but what happens is the energy losses come in through the velocity, right? So either you add or lose velocity. Now, of course, this is not always true, but generally we're not going to be changing the potential energy that's based on height and position. Of course, there are not extreme, but there are cases against this, but just generalizing here some of the cases that you might see. And honestly, with AP Physics, we're just going to worry about friction. So remember, work in its basic definition is force times d times cosine of the angle. And then if we're talking specifically about friction, then it's going to be the force of friction times d times cosine of the angle. And really, this cosine of the angle gives you the direction of the force, which always is going to be opposite. So you can even simplify this by just doing negative friction, or the energy is being taken away, and just ignore the cosine. But either way, it works. So why don't we go ahead and actually figure out, how to use this, how to use energy when you solve these problems. So these are actually kind of like kinematic questions. We could do this with forces, but we're going to do the same question with energy now. So suppose you push a block that's 10 kilograms of mass with an initial velocity of 3 meters per second. How far does the block move if the coefficient of friction between the floor and the block is 0.45? So here's the scenario, right? So let's draw a picture. So we have our block, and we pushed it, so it gave it an initial velocity. So the initial push is gone. So the initial velocity of 3 meters per second. We know that's going to go some distance before it comes to rest over here sometime later, right? Excuse my terrible drawings here. Because we know that friction will, eventually stop this, right? And that is surprisingly all the information we have, right? So, as always, let's analyze the system. So we have an initial, so I'll call this the initial, as you know. This is where I call my initial point and my final. So let's think about the initial conditions. So, so far we just have initial velocities, and notice that we're not, we actually have no height, really. We're not changing our potential energy actually at all. So there's no height difference between the two places. And then we have no spring, so let's just be silly and just consider it. There's no stretch of a spring. So really, there is no potential energies, right? So they're pretty much gone here. So, like I said, I kind of like the other version better, even though I have it here, but we can work it out this way. That's fine. Okay, we'll keep going with this. So if you notice, I'm using this version of that, which is fine. So if you notice that the final kinetic energy of the system is going to be 0, so this actually goes to 0. So let's rewrite this whole thing, okay? So it says negative, so that's 0, that's basically 0. I mean, that's technically 0 too, and that's 0, right? So negative kinetic energy initial is equal to the work done by the non-conservative force, right? By the way, we're looking for how far, right? How far. So that's actually the variable d. Is equal to the work by the non-conservative force. So, if you think about it, as you might notice, is that friction is involved in this. There is a force of gravity, there is a normal force, and I know there's a velocity vector here. It should be I'm just going to scribble this out because I can't really erase with this pen, unfortunately. I'll just put that velocity vector there. But anyway, you can see the force diagram. So friction, as you could tell, the work it's going to be done by friction. So negative Ki is going to be equal to the negative work done by friction. And as you can see, the negatives will cancel each other. Now the negative sign comes from the fact that the distance is forward, the force is backwards, which makes it a cosine of 180, which pops out a negative sign. So I'm considering the angle right here. So the negatives go away, and then I have 1/2 mv initial squared equals the force of friction times d. And I hope you noticed that basically one way for me to really, I could have just started here if you notice. I could have said that the all of the initial energy goes into the work done by friction and just start here. I actually prefer this method. I like writing my own equations, but that's okay. So you need to know the force of friction. So side note, the force of friction is going to be force normal times mu. Now, since the normal force, since we're on a level surface, the normal force will equal the force gravity. So mg mu. Sorry, my mu is really terrible, but that's a mu. So I'm going to go ahead and keep going. 1/2 mvi squared equals. So the force of friction is going to be mg mu d, like that. And as always, usually we have our masses canceling out, and we're looking for d. So I'm running out of space here. I'm just gonna rewrite this. So I get 1/2 vi squared equals g mu d, and d is gonna be v squared over 2g mu. And there you have it. That is what we need. So essentially, the distance depends on the coefficient of friction, the force of gravity, and how fast it initially started. So hopefully that makes some sense. And just to calculate this value, sorry that I'm all over the place, I'm just running out of space. So the velocity is 3 meters per second. We're going to square that. No 2, 9.81 in mu, which is 0.45 in this case. So let's see, 3 squared. Oops, hold on, my calculator's being weird. Okay, 3 squared divided by 2 divided by 9.81 divided by 0.45. So I go a whopping big distance of 1.02 meters. So friction has a pretty good, hold on this, showing it doesn't go very far like that. So this is how you could do kind of like a kinematic equation problem with energy instead. And like I said, I very much prefer this over forces and kinematics because usually it's a lot more simple. So that's how you can use energy of finding how far a block has gone after pushing it, right? So that's one way we can look at this. Another way to interpret this is to look at the bar graph, right? So it's kind of what I said initially, that we start off with just kinetic energy, and then this is the friction, right? But it's taking away energy from the system. So notice that it basically counters itself, right? We start off of having some initial energy in the system, and then notice that there's no energy final. Now I hope that makes sense because the block stopped, right? So the energy just gets transferred, right? So again, even though the system loses energy itself, the energy goes into something else. This goes into like the floor, not back into the block or whatever it was that was moving in this case. So Anyway, you could see that, you know, if this was like plus, you can't see that, plus 5, this is minus 5, and the energy's here. So this is just another way to model what we just saw kind of in that, you know, that previous example using a bar graph. Okay, so here is another case. The most common cases is this. So we have a block of mass M. It slides down a frictionless incline, comes back, and it comes to rest some distance after traveling the length of the incline. How far does the block go? So essentially we're asking, it's, you know, looking for this once again. So let's solve this algebraically, you know, with no numbers, just to kind of get a sense of how to do this. So there are multiple ways to do this. You can honestly do it a few different ways. I'll show you one way. I'll show you the first way you can do it, where it's kind of writing the equation. So I'm going to call this the initial condition. And actually, right here at the end, I'm going to call this my final. Oops. So, as always, let's analyze what we have. So we definitely have an initial height here. Now, it doesn't say otherwise. I'm kind of looking for it. So we can assume that it started at rest. It doesn't say it had a velocity to begin with. So we can assume that our initial velocity is 0. And then there's no spring, so I'm not going to even consider it. So that's our initial conditions. Our final conditions is that the height f is in fact 0. Our velocity is in fact 0. But what we can say is that there is, you know, some distance due to work by friction. So let me show you how I'm going to write this out. So I'm going to say all of the initial potential energy goes into the work done by friction. Because the energy has to go somewhere, right? So what will this look like? So I have mgh I is equal to the force of friction times the variable in this case is x as such. Okay, so turns out that friction is actually only present from here to here. So that's actually good. If it was the whole incline, which it's not, but let's pretend it was, then the whole incline would have to, you'd have to include this. You'll see the next example how I'm going to do that. Now, alright, so I'll stay with this. So anyway, so the friction really acts in this location right here. So I can keep going. Now, I just noticed in this exact question, it doesn't actually give you HI at all. It gives you this angle. And it doesn't actually give you L either, which is kind of silly, to be honest. But just, why not? I'll add a factor of L so that I can use the angle. So if I don't have HI, notice that it could be L sine of the angle, right? Because this is opposite the H. So I can write mg L sine of the angle, where this represents HI. This goes into the work done by this little teeny tiny part. Just like I explained before, this is level, so anytime your friction's level, when you do force normal times mu, this is going to be mg mu for level surface. That's because on the block right here, you know, the force normal will equal force friction. I'm sorry, force gravity. So the force of friction on that level surface there, because that's the only place that the friction is present, is going to be mg mu. I'll use mu k because that's the way it's written here, times x. So essentially the answer is basically solving for x. Looks like this. You can cancel out the masses. Actually, Fun, you can cancel out masses and g. So what you get is L sine of the angle is equal to mu k x. L sine of the angle over mu k is equal to x, just like that. So how far it goes depends on how long basically how high you started and the impact of friction, just like that. So that's another way you can solve a problem like this, assuming that they gave you L in this case. Let's do one more. Oh. Anyway, by the way, this is just, I forgot about the slide. But this is just kind of very similar to what we just did, if you noticed. That you start off with all potential, just like I kind of pointed out before. And the kinetic goes into the work, which is fine, but I did a shortcut. If you notice, I started with potential and went right into the work done by friction, and said that all the potential just went into the work done by friction. Now you could have done the previous problem. This is one way to solve it. You could have done it, say, starting here, by the way. And then the other option is to say that, to say that the kinetic energy at the bottom goes into the work done by friction, and what you'll notice, you'll get a very similar answer to what we just did. In fact, it would be the final velocity at the bottom, 2g mu. These are both similar answers. They're expressed differently with different variables, but that's the same answer, really. Well, it should give you the same answer. But more importantly, notice that the energy of the system gets lost as it slows down, right? Because we're taking away that energy. So the final energy at the end of the whole system goes to 0. Okay, one more. This one has numbers and it's a little more complicated because now we have friction on the incline. And then again, we're kind of using the same kind of concepts here. So let's see, let me take a look. So we start at rest, it slides down a 22-degree incline. And the incline is 75 meters long, which is actually referring to this measurement here, the ramp itself. That's actually an important measurement. If the coefficient of friction is 0.09, what is this, the skier's speed at the bottom? And then the question is, you know, how far did it go? This delta, this x right here. Okay. So, so same thing. Now we have a height here, right? So I'll call this the initial. For part A, this will be my initial, and this will be my final. So I'm going to call this F, VF right here. There's no height final here. There's no springs. We're not going to even consider it. They don't give us HI, if you notice, but like I said earlier, we can find that out. HI is going to be L sine of the angle right here. So I'll plug that in a little while. But notice that we have friction coming into play here. So I can write my expression this way. Yeah, I can write my expression. Sorry about that pause. Let me just start over here. So we do have some height here. We have friction, and we're going to slow down. So let's write out our equation. So we start off with potential energy minus the work done by friction equals the kinetic energy. As such. Okay, so I'm going to go ahead and start plugging more values in. So what I have now is mgh, mg, sorry, L sine of the angle. Okay, so work done by friction. We know that work done by friction is going to be force friction times d. For inclined planes, I'm going to make a jump here. The force normal times mu times d. The force normal for inclines is mg cosine of the angle. I'm just going to assume that you know how and why I got that, and if you don't, you can always ask me, but that is for inclines, the normal force on this case. So this all goes in here, mg cosine of that same angle, this is the same angle, mu d equals 1/2 mv final squared, which is, of course, the v is what we're looking for here. As always, see that there's no mass here, so all the masses do cancel, which is helpful. Like that. And essentially we're solving for v squared, so we're going to go ahead and just happily plug in some numbers here. L is 75, this is sine 22 minus, so we're taking away energy from friction. Yeah, it's just a lot of numbers. It's actually not too bad. And the d is how far it went. So this is just on the incline, so this is the 75 meters part. Okay, so this is just me plugging in numbers. How fun is that? So 75 times sine 22. So this is 275.62 minus 61.4. This actually, the units actually become meter squared, second squared. I'm being kind of lazy about my units right now. I just want to get a number. So two 214.25 equals 1/2 v squared times 2. So 428.5 equals v final squared. Square root of the answer. Perfect. V final is 20.7 meters per second. Okay, that is the correct answer, so that's always good. So if you notice I started with this, you actually could have honestly wrote it similar to the way I wrote it before. You can actually rewrite this as mgi is equal to, if I move this over, it becomes positive. So you could have done it as a positive value here. This is also okay. But notice that if I did it with it over here, it makes less algebra if you notice. So that's kind of why I did it the way I did. But this is also acceptable too. That you're saying that the initial energy goes into work and it goes into the motion of the object. So that's definitely, one way to do this. So notice that, I cut it off halfway too, right? I didn't actually use the whole problem like that. So that's another thing to think about, is you can start and end anywhere you want. So that's the beauty of this topic too. And just to show you, let's say without friction, just really quickly, mgh equals 1/2 mv squared, right? This is without friction. 2gh is the velocity. So I just want to show you what that number is. 2 times g times L, so 75 times sine of the angle. Square root that answer. So with friction, without friction, this is about 23.4 meters per second. So this is without friction. So as you can see, it's not a huge difference, but it does do what it's supposed to do, which is move slower in the presence of friction. So there you have that. Alright, now let's look at part B. Honestly, the easiest way I would do this is, since we have the velocity right here, we have the final velocity of 20.7 meters per second, and we know that eventually we'll go to rest here. I would just start here and end here, saying exactly what we've been saying, is that the total energy, kinetic energy, even though I'll put it F here, goes into the work done by friction. That's exactly how I'd solve this. Since it's a level surface, we can just write mg mu for friction. I'll actually use the variable that they have, but just know that the d is actually just x. So this goes away. We have mu from before, and then x is again that v squared over 2g mu. Hope you don't mind that I shortcutted that. So this becomes 20.7 meters per second to g 9.81 and 0.009, which was our mu from previously. Now in the previous problem it said that mu was the same. So, I almost forgot to square it. There you go. That would have been pretty bad. Okay. 20.7 squared divided by 9.81 divided by 2 divided by 0.09. Oops, that didn't work. Let me try that again. 20.7 squared divided by 2 divided by 9.81 divided by 0.09. There we go. Perfect. How far did it go? It went 242.66 meters, like that. That is actually the easiest way to solve that. As always, you could have started at the beginning and did the same thing, but if you started at the beginning, you have to consider the friction of this whole thing too, which is a little more complicated. Doable, but just more complicated like that. So this is, I would just say, this is the easiest way if you just start here like that. So this concludes our analysis with non-conservative forces and energy systems. I find that writing the equation is actually the best way, and just understanding your energy and where they're present, that's the best. Alright, let me know if you have any questions and I'll be happy to help you.